Welcome to Pre-Calculus. Today we will investigate analyzing exponential functions. We'll take a look at two examples. Our first example is this function for which we've got a graph and some information about how it would be formed from a parent function. So our goal here is to do really four things. I want to determine the domain, determine range, determine end behavior, and then the last thing is to write an equation for this graph. Let's start with the domain and the range. So one thing we got to recall with domain is really what it's describing for the graph. Domain describes the x values of the graph. So when we've got a coordinate plane like this one, we're really looking from the left-hand side to the right-hand side. So when we're trying to analyze for domain, we're really investigating what's happening to the graph on the extreme left and on the extreme right. So on the extreme left, it's got an arrow that's really mostly headed in the left direction. Horizontally, that's headed out to negative infinity. On the right side, the arrow is really mostly going in an upward direction. But even as it travels up, it's drifting to the right. And although it's a slower travel in that direction than it is to the left, it is headed out also towards positive infinity. So for domain, for an exponential function like this one, we would have from negative infinity, less than x, less than infinity. We could write that in a couple different ways. I could put it also in interval notation, parentheses, infinity, comma, parentheses, infinity, parentheses. So note that form just takes out the variable x as well as the inequality symbols. And then I could write it in words as well, all real numbers. And that usually is the domain that we would expect with any exponential function that has no restrictions on its domain. Well, if domain is a description of the x values left to right, range is a description of the y values of a function. So on a graph on a coordinate plane where we're looking to determine range is the lower part and the upper part of the graph. So I see that this function does not continue to go in a downward direction. This left-hand side is really minding what we call a horizontal asymptote. So with exponential functions, we're always on the lookout for the horizontal asymptote. And it's an invisible line that the function gets close to but never touches or crosses. And it really affects the range. So we're seeing with this graph that it does not have any points that would have y values less than -2. So as I write range, the lower limit for this function is going to be -2. That's less than y. And then if I look at the upper part of the graph, again, I'll double circle that so that we can consider what's happening there. In the vertical direction, that really is headed to positive infinity. There's no restriction like the horizontal asymptote at the lower part of the graph. So in inequality notation, the range is from -2 to infinity. And we would always expect some integer or rational number as part of the range, or an irrational numbers, but something real and not infinity. And that has to do with the horizontal asymptote. In interval notation, that's parentheses -2, comma, infinity, parentheses. And we would put parentheses on both the left and the right because the function never actually equals -2. It just gets very close to it. The last part of the analysis before we write the equation is the end behavior of the function. And really that's an answer to the question, what is happening to y on the extreme left and right of the graph? So it's a little different than domain and range because it's putting together those two ideas. We're trying to say what's happening to y at the extreme left and the extreme right. So one way we can write it is in infinity notation. So really what we're trying to do here is match up our domain and our range. So I'm looking here on the left-hand side of the domain, negative infinity. So as I write this statement about end behavior, the way I would begin it is as x approaches negative infinity, y approaches, and I can see on the graph that as we're headed out there on this left side of the graph, the y value is approaching closer and closer and closer, -2. And we saw that when we were analyzing the range of the function based on the horizontal asymptote. So notice we're kind of putting together domain and range here. So then we want to consider the far right side of the graph as x approaches positive infinity. So I'll box that. Y also approaches positive infinity. So the pieces of the domain and the range help us to write the end behavior statement. Our last task is to write an equation for this function. So what we got to use here is this information that's at the top of the graph that's talking about the parent function and various transformations that have been carried out on the parent function to make this graph of the blue exponential. So we're working based on the template f of x equals a times b to the power of x minus c plus d. And what we want to fill in, if it applies, are these four numbers. So a number for a, for the base b, for the left to right movement c, and for the up down movement d. So basically what we need to do is fit in the information we have here in words into the equation. So we're first told the parent function's f of x equals 2 to the power of x. That information always tells us about our base. So I'm going to put that the base b is 2 to the power of x. So I'm building this equation below here. And we'll call this g of x since it is a descendant or a family member of the parent function. I have two translations. One is left to. So that is this C term. This describes left or right translation. And what we need to know about that C is that the sign in the equation is opposite the direction that it actually traveled. So if we're going left to, typically left is about the negative symbol. So if I'm putting what's opposite, I'm going to write plus 2. So that would describe a translation 2 to the left. The second translation's down 2, and that's described by this plus d. That we actually follow the sign, which would tell us the up down. So if we have gone down 2 from the parent function, I'm going to write minus 2. The last thing that is in our data here is that I've got a vertical stretch by a factor of 4. And that's always going to be this multiplier a out in front of the base. So I'm going to write 4 there. And that's my equation. Now, one thing we can do to check is to just look at our equation as a graph. So I'm going to take this proposed equation 4 times base 2 to the power of x plus 2 minus 2. And I just want to input that into the graphing calculator to see, does the graph that I can create there look like what we have here? So let's go to Desmos really quickly just to check our answer. So we'll type in g of x equals 4 times base 2 to the power Desmos, you always have to use parentheses for the power, minus 2. And that looks like a really good match to the graph that we had presented to us at the outset. So our equation looks very accurate to the graph that we're given. All right, we'll take a look at our second example. Our second example is this function given here. So notice the changes in the function. This one is mostly in quadrants 3 and 4. And we're told that its parent function is the half base, so half to the power of x. We want to do the same things to begin. We want to find domain, range, and end behavior. So we'll start with those tasks. Again, domain is a description of the x values, left to right of the function. So again, I want to look at the extreme sides. So that left side is mostly traveling in a downward direction, but it's also drifting slowly to the left towards negative infinity. The right side is also more clearly even headed to the right towards positive infinity. So again, we're not surprised that our domain is going to be negative infinity less than x, less than infinity. In interval notation, parentheses, negative infinity, comma infinity, parentheses, or in words, all real numbers. So again, the domain is typically just that, all real numbers for an exponential function. But recall the range on an exponential is really limited by either a ceiling or a floor represented by the horizontal asymptote. So I see our horizontal asymptotes going through -1. And again, you can kind of locate that asymptote just visually by seeing what number is the graph approaching on one side or the other. It'll always be tending towards a single number. So as I think of this function from the lower part, it actually is decreasing infinitely. So it's headed towards negative infinity in the negative direction. But in the positive direction, this graph really mines the horizontal asymptote at -1. So my way of writing the range would be negative infinity less than y less than -1. Again, on the range for an exponential, you'll have an integer number, or really a real number instead of just headed out to infinity. And we can translate that to the interval notation. Again, the last thing for us to finalize here with the analysis is the end behavior. And I always like to think of this as an answer to the question, what is happening to y at the extreme left and right of the graph? And again, we can use our domain and range to help. So again, if I'm thinking of the far left side of the graph as x approaches negative infinity, y, if I again pair up my domain and range, y, and we're talking about this lower side here, the y value is approaching negative infinity also. If you could imagine that there was a car driving on this graph, if it was headed to the left, it would ultimately turn and travel mostly in the negative y direction. And then finally, as x approaches the other side, so if we turned our car around and drove to the right side, positive infinity, there our y value is going to get closer and closer and closer to the horizontal asymptote at -1. So y approaches -1. That concludes our analysis. The last thing for us to complete here is the equation. So again, I'll put that template, g of x equals a times the base b to the power of x minus c plus d. So I got the base here for the parent is going to be half to the power of x. So we'll fill in with that. So it's going to be half for the base to the power of x. You always build on your parent function. So again, this is g of x. And then I see I have a translation again, left 1. So remember, that's opposite the sign. Left is normally minus, so opposite would be plus 1. That goes in the power. Down 1, we follow the sign. Down direction is typically negative. And then we've got a vertical stretch by a factor of 4. That's my a term. But notice I have two additional pieces of information. Well, one additional piece of information, a reflection across the x-axis. Our reflections could show up in two spots. They're always governed by a negative sign. They could be in front of the a or in front of the x. So the one that would reflect across the x-axis is this lower one, the one that would multiply in front of the equation. So since that's what we've got, we're going to put a negative out front of the 4. And that should reflect it across the x-axis. The other spot that's highlighted in green up by the exponent would create a reflection across the y-axis. So we'll box that equation. And again, we just want to make a visual inspection by taking it over to Desmos and just plugging it in and comparing that graph with the one we've got here. So we'll head over there. And again, it's just a good check to take your newly created equation and go back into the calculator to graph it. So negative 4 times base 1/2 to the power of x plus 1, and then minus 1. Excuse me. And that looks great. Our equation is a faithful representation here on the graphing calculator to the graph that we had in our example. Well, thank you for joining for this investigation of analyzing exponential functions. See you soon.